Hi, this is Pasha, and we are finally here with the second lecture of SI base units. And in this lecture, we are going to discuss about the homogeneity in equation. Now, before we move on to this lecture, I just wanted to tell you that we already have lecture number 1, and I hope you have already watched that, in which I explain you how to figure out the SI base units of different physical quantities or different derived quantities. What are the rules? And I discussed like approximately 20 to 22 examples of common examples of derived quantities and figured out their SI base units. Now this is the next step. Now we are moving on towards the homogeneous equation, or what is the homogeneity equation. Now there are few important points that you all need to remember, and the first point is that in order for an equation to be true, it must be homogeneous. So if an equation is not homogeneous, it is not true. Simple as you like. Now what does it mean to say that an equation must be homogeneous? So the next point is that in a homogeneous equation, the SI base units of all the terms are same. Right? Not all homogeneous equations are true unless they are experimentally verified. Alright, so the first step, you see, in physics we do not accept any equation unless it is experimentally verified. But before we move on towards the experiments, we first check the homogeneity. You see, homogeneity is the first step. If you can't fulfill that rule, there is no need to go for the experiments. Alright, so if an equation is not homogeneous, then that equation is not true. Now again, I have written these three statements that in an homogeneous equation the SI base unit of all the terms are same, but the actual meaning you will understand after we see some examples. Now on your screen you have been given three equations of motion, that is v equal u plus at, s equal ut plus half at square, and 2as equal v square minus u square. These are the famous equation of motion. They are all true equations, and in these equations there are total 5 variables. We have v, u, a, t and s, where v is the final velocity, and you know it doesn't matter whether the velocity is initial or final, that will be measured in meters per second. Similarly, initial velocity is also measured in meters per second. Acceleration, we have seen that it is measured in meters per second square. Time is measured in seconds, and displacement is measured in meters. Now let us check for the homogeneity of these equations one by one. So first of all, I am going to start off with v equal u plus at. Now you see, v is final velocity, so in place of v I will write meters per seconds. U is initial velocity, so I will write again meters per second as the SI base unit of u. Now acceleration is meters per second square, and time is seconds. Alright, so in place of time I will write seconds, in place of acceleration I will write meters per second square, in place of u I will write meters per second, and in place of v I will write again meters per seconds. Now if I further simplify these equations, what I will get is meters per seconds equals meters per seconds plus this square and this second will cancel out each other, and again I will be left with meters per seconds. Now you can see that all the terms in this equation, you see this term or this term or this term, all the three terms have the same base unit, that is meters per second, and meters per second. If any of the term had a different SI base unit, it would not be called as a homogeneous equation. So now I can say that v equal u plus at is a homogeneous equation, and the reason is simple, because all the terms have the same SI base unit. Now moving on towards the next equation, which is S equal ut plus half at square. So let's say here I have S equal ut plus half at square. Now you all know that S is displacement and we measure displacement in meters per seconds. U is initial velocity, we measure that initial velocity in meters per second. Time is measured in seconds, plus 1 upon 2 is a constant number. We have already seen that we ignore a constant number in an equation while figuring out the SI base unit. So we are going to ignore that 1 upon 2. In place of acceleration, I will be writing meters per second square, and in place of time square, I will be writing seconds square. Now again, this second will cancel out this second, and this second square will cancel out this second square. Again, I'll be left with meter equal meter plus meter. So now again, you can see that all the terms have the same SI base unit, that is meter, meter and meter. So again, I can say that yes, this is a homogeneous equation. So in a homogeneous equation, all the terms have the same SI base units. Now moving on to the next example, if you look back at the example, that's again 2as equal v square minus u square. So if I try to figure out whether this equation is homogeneous or not, so I will write 2as equal v square minus u square. Now since 2 is a constant number, so I will ignore that 2, and because we do not consider the constant number in an equation while figuring out the SI base unit, in place of this acceleration, I am going to write meters per second square, which is the SI base unit of acceleration. In place of displacement, I am going to write meters equal final velocity we measured in meters per second square, meters per second, but because I have a square, so I'll put a square over here, minus initial velocity is also measured in meters per second, so I will put a square over here too. Now this is going to be meter into meter, as meter square per second square equals again, this is going to be meter square per second square minus meter square per second square. So now again, you can see that all the terms have the same SI base units. So if all the terms have the same SI base unit, then again you can see that this equation is a homogeneous equation. So this equation can be a true equation. Obviously the final decision whether the equation is true or not will be taken after doing the experiment. But before the experiment, we check whether the equation is homogeneous or not. So we can see all these equations have turned out to be homogeneous equation. And the reason being is that all the terms have the same SI base unit. Now we are also familiar with another equation, which is, if you remember, the equation of wave, or the wave equation, which is v equal f lambda. Now again here, if you remember, v was the speed of the wave, f is frequency, and lambda is wavelength. So we measure speed, doesn't matter it's speed of wave or whatever, as long as it is linear speed, we are going to measure it in meters per seconds. Frequency is measured in 1 upon seconds, and wavelength is a length, so obviously that will be measured in meters. Frequency is 1 upon t, so 1 upon seconds. Now solving for this equation, in place of v, I am going to write meters per seconds equal. In place of frequency, I am going to write 1 over seconds. In place of lambda, I am going to write meters, because that's again a length. So again, I am left with meters per seconds equals meters per seconds, and that pretty much makes sense, because again, all of the terms have the same SI base units, which is meters per seconds. Now there can be some trick examples also, so we are going to consider that example too. Alright, so now moving on, this is a very good example to discuss with to understand the concept of homogeneity. We have this very famous Bernoulli's equation, which is not the part of the A-level curriculum, but still that's a very interesting and a very famous equation. That is P plus rho g h plus 1 upon 2 rho v square equal k. Now they have given this equation and they have given the meaning of every equation. So they said that P is pressure, so this P is pressure, H is height, rho is density, g is acceleration due to gravity, and then again rho is density and v is velocity. And what we have to do is that show that the equation is dimensionally consistent and also the SI base unit for k. So let us try this equation. So if I move on towards solving this equation, I have this pressure, and we know that we have the SI base unit of pressure is, you see, pressure is force over area. We measure force in kilogram meters per second square and area in meters square. So this will sum up to get kilogram per meter per second square, because this meter and square will cancel out each other, and I'll be left with kilogram per meters per second square. So this is the SI base unit for pressure. And the next thing is density. So we know that density is mass over volume. So mass is measured in kilogram and volume is measured in meter cube. Alright, and then the rest we all know that g is acceleration due to gravity, and that is measured in meters per second square, and height is a length, obviously that will be measured in meters. So I'm writing this equation again here. So what the equation says that P plus H rho G plus one over 2 rho V square equal K. Alright, so you can see that this is the equation, P plus H rho G plus 1 over 2 rho V square equal K. Now if I try to check whether the equation is homogeneous or not, I'll start putting on the values. Now you can see that this P is pressure, so in place of this P I'm going to write kilogram per meter per second square. We just figured out this. See, this is the SI base unit of pressure, kilogram per meters per second square. All right. Now then plus, in place of this H, this height, I'm going to write meters. In place of this density, I'm going to write kilograms per meter cube, because that is mass over volume. In place of this G, gravitational acceleration, because this is acceleration, so I'm going to write meters per second square. Plus, again 1 upon 2 is a constant number, so I'm going to ignore that 1 over 2. But in place of this rho, which is density, I'm again going to write kilograms per meter cube. In place of this V square, because V is velocity, so again I'm going to write meters per second in place of velocity, and because I have a square over here, so I will put on the square here. And I don't know the SI base unit of K, so I'll leave K as it is. Now simplifying it, I'll get kilograms per meters per second square equal. Now you see this meter and this meter, they will multiply to get meter square and then divide by meter cube. I'll be left with 1 meter on the denominator. So this will be plus kilogram per meters per second square. Now here again I have this kilogram that I will write as it is. This second has a square, so that will be second square as it is. But this meter square and this meter cube, they will cancel out each other, and I will be left with a meter in the denominator again. So again simplifying this, I will be left with kilograms per meter per second square. So now you can see that all the terms have the same SI base unit. You see, this term and this term, all the three terms have the same SI base units. It means that they are dimensionally consistent, or they are homogeneous. Homogeneous equations are also called as dimensionally consistent equations. Alright. And obviously if all these three terms have a unit of kilogram meter per second square, then eventually the SI base unit of K will also be equal to kilograms per meters per second square. So this was a good example to practice on with, that is available on my worksheet too. And now I have another very good question to discuss with you. Now moving on towards this question, it says that the heat capacity C of a solid can be expressed as a function of temperature T. So this T is temperature, and that fits the expression C equal alpha T plus beta T cube. Find the possible units of alpha and beta. Now if you look at the previous questions or simple questions of SI base unit, if we want to figure out the SI base unit of an unknown quantity, so what we do is that we make that quantity as subject. The problem in this question is that I have alpha and beta as two unknown variables. So if I try to separate alpha, I cannot make beta as the subject. You see, if I try to make alpha as the subject, then I will have alpha in the form of beta. If I want to make beta as the subject, then I will have beta in the form of alpha. But from one equation I need to figure out both the SI base unit of alpha and beta. Now the concept of homogeneity applies here very well. So look at how I'm going to solve this question. Now first of all, this C is the heat capacity. Alright, so first of all we should know what is heat capacity. So heat capacity is Q over delta T, which is the amount of energy provided per unit rise in temperature, and that is equal to, you see, energy is kilogram meter square per second square. This Q is energy, and delta T is temperature, change in temperature measured in Kelvin. So we have already seen that, so I'm not going to explain that in detail, and I will be left with kilogram meter square per Kelvin per second square. So this is the SI base unit of C, right? Now moving on towards this question, that C equal alpha T plus beta T cube. See, in place of C, I'm going to write this kilogram meter square per Kelvin per second square equals. In place of alpha, because I don't know alpha, I'll write alpha as it is. In place of T, because T is temperature and I know the SI base unit of temperature, so I will write Kelvin plus beta as it is. T is again temperature, so I will write Kelvin power 3 because there is a cube here. Now what is important is that if it says that this fits the expression, if it says that the equation is true, then all the terms must have the same SI base unit. So this term and this term and this term, all of these three terms must have the same SI base unit. So now look carefully. This is one term with the SI base unit kilogram meter square per Kelvin second square. This is another term alpha Kelvin, then this is another term beta Kelvin cube. What I can say is these two terms must have the same SI base units. So just for the sake of SI base units, I can write that kilogram meter square per Kelvin per second square should be equal to alpha Kelvin, and that would eventually give me the SI base unit of alpha, which is kilogram meter square per Kelvin square per second square. This Kelvin getting multiplied with alpha, when it moves to the left hand side it will be divided and it will make Kelvin as Kelvin square. So here I have successfully figured out the SI base unit of alpha. Similarly, I can say that this term and this term must also have the same SI base unit. So what I am going to do is that I am going to write here as kilogram per Kelvin per second square is equal to beta Kelvin power 3. Now what I am going to see here is that beta is equal to kilogram, sorry, I will need to have a meter square here, kilogram meter square per Kelvin power 4 per second square. And this is how, my friends, I am successful in figuring out the SI base unit of both alpha and beta using only one equation. I've been successful in figuring out the SI base unit of both alpha and beta, and the reason is that every term has the same SI base unit. So this rule of homogeneity is a very handy rule in figuring out the SI base unit of the unknown variable. Now there is one more tricky question, or a different type of question that is often asked in exam. Alright G. Now in order to solve this question, you need to be a little good in base units and also in basic mathematics, or if you have good understanding of how to solve equations involving indices, then probably this is going to be an easy question for you. So it says that the time period t of a simple pendulum is determined by using the equation t equal k l raised to the power x and g raised to the power y, where l is the length of pendulum, g is acceleration due to gravity, and k is a dimensionless constant. When it says k is a dimensionless constant, it means k has no unit, so you can ignore k as a constant number in the equation. And now determine the value of x and y. So what they want is from you is to figure out the values of x and y. Alright. So let us start solving with this equation. So I have t equal k l raised to the power x and y. So in place of this t, I am going to write seconds, because time is measured in seconds, equals k is a dimensionless constant, so I am going to ignore k. I am not going to write any SI base unit in place of k, and then L is length, so length is measured in meters, so I am going to write meters power x, and then just g is meters per second square, because that is acceleration, so it is measured in meters per second square, and it has the power y. Now so with this equation I need to figure out the values of x and y. So let's see how I'm going to do this. This s equal meters power x, meters power y, and seconds power 2y. Alright, so this y will get multiplied to the power of both meters and seconds. So meter power y is meter y, second square power y is second power 2y. Now this equation can also be written as s equals meters power x, meter power, in fact I have meter power x, meter power y, so I can write meters power x plus y, because when two terms get multiplied with the same bases but different powers, so we add the powers. So m raised to the power x and m raised to the power y is equal to m raised to the power x plus y, and this second will be power minus 2y, because I have moved this second power 2y from denominator to the numerator. Alright, now I need to compare the left hand side and right hand side. The problem is that on left hand side I do not have meters. So what I can do is that I can multiply the left hand side with 1. Now this 1 will help me introduce, obviously that won't affect the equation, but this help me introduce meters like this. See, in place of 1 I am going to write meters power 0. Obviously anything power 0 is 1, so still that won't affect the equation, but now this will help me to compare the powers on the terms on left hand side and right hand side. So you see that on left hand side this meter has power 0 and this meter has power x plus y, so I can say that 0 is equal to x plus y. Similarly on left hand side the power of s is 1 and this power of s is minus 2y, so I can write that 1 is equal to minus 2y. So here I'll get y equals 1 over 2, and here I have, since I know the value of y, so now I can use this equation as x plus minus 1 over 2, and that would give me x as minus 1 over 2, and this is what I needed to figure out the values of x and y. If we go back to the equation, it says find the value of x and y. Now with these examples the concept of SI base unit is over. So the first step is that you learn to figure out the SI base units of different physical quantities, and then you learn to play with these homogeneous equations, and then you can move on towards solving the past papers questions. I hope this video will surely help you out in solving and understanding the concept of SI base units. Thank you very much.